The Unification of Gravity and Electromagnetism. Einstein, Veneziano, Witten, the ultimate theory of everything. Imagine standing at the edge of reality, looking beyond the fabric of space and time, searching for a single equation that unites everything. For centuries, physicists have sought a grand, unifying framework, a theory that explains both the immense force of gravity and the delicate structure of electromagnetism. It is the ultimate question. How do the fundamental forces of nature weave together to form the universe as we know it? The journey toward unification has been driven by some of the greatest minds in history. James Clerk Maxwell first unified electricity and magnetism into a single force, electromagnetism. Albert Einstein revolutionized our understanding of gravity with general relativity, but he spent the last decades of his life trying and failing to merge it with electromagnetism. The early 20th century brought new attempts, from Kaluza and Klein's hidden fifth dimension to Satyendra Nath Bose's quantum statistics, which hinted at a deeper connection between fields and particles. But the real breakthrough, the key that unlocked an entirely new way of thinking, came not from Einstein, but from a young physicist in 1968, Gabriele Veneziano. He was not trying to solve the mystery of unification. He was simply searching for a mathematical equation to describe the strong nuclear force. What he found, instead, was something astonishing. A function that perfectly described particle interactions, but in a way that suggested something deeper. A hidden structure of the universe, something vibrating, something fundamental. Without realizing it, Veneziano had stumbled upon the earliest version of what would later become string theory. The quest for unification. The unification of forces is not a modern ambition. The story began with Maxwell, whose equations showed that electricity and magnetism were not separate phenomena, but two aspects of the same force. Maxwell's work led to the realization that light itself was an electromagnetic wave, a profound revelation that brought clarity to the nature of the electromagnetic spectrum. But what about gravity? Einstein's general relativity was a masterpiece of mathematical elegance. It showed that gravity is not a force in the conventional sense, but the curvature of space-time caused by mass and energy. And yet Einstein was dissatisfied. The universe, he believed, should follow a single, harmonious set of laws. If electromagnetism and gravity were both fundamental forces, then nature should reveal a way to unify them. Kaluza and Klein proposed a bold idea. What if an extra unseen spatial dimension existed beyond the three we perceive? If this fifth dimension were real, then Einstein's equations could naturally include electromagnetism alongside gravity. The problem was that no one could detect this extra dimension. Without experimental evidence, the idea faded into obscurity. Meanwhile, the rise of quantum mechanics introduced a new complication. While electromagnetism could be described in the quantum framework of photons and electromagnetic fields, gravity stubbornly refused to fit. Attempts to quantize gravity led to mathematical infinities, nonsensical results that suggested something fundamental was missing. Physicists were stuck. The forces of nature were known, but they would not merge. The birth of string theory. Gabriele Veneziano was not thinking about unification when he made his discovery. He was studying high-energy collisions, trying to explain the bizarre patterns emerging from particle accelerators. He found a peculiar equation that perfectly described the experimental data. But when physicists examined it more closely, they realized something shocking. The equation described a force mediated not by point particles, but by extended vibrating strings. What does it mean for the fundamental building blocks of nature to be strings instead of point-like particles? Imagine plucking a violin string. Different vibrations produce different musical notes. Now, imagine a string so small that its vibrations determine whether it manifests as an electron, a photon, or even a graviton. The hypothetical quantum particle of gravity. The realization was profound. If fundamental particles were actually tiny vibrating strings, then perhaps the reason gravity refused to fit into quantum mechanics was that physicists had been thinking about it the wrong way. Instead of a separate force, gravity might emerge naturally from the vibrational patterns of strings. This was an entirely new perspective, one that suggested that all forces, all particles, and all interactions were just different expressions of these tiny vibrating entities. Why string theory might be the only answer. Despite its elegance, string theory faced a significant challenge. The equations only made sense in 10 dimensions. This was a problem. Our universe appears to have only 4 dimensions, 3 of space and 1 of time. But what if the extra dimensions were hidden, curled up at an unimaginably small scale, beyond our ability to observe? Edward Witten, one of the greatest physicists of the modern era, pushed string theory even further. He proposed M-theory, which unified 5 competing versions of string theory into a single, coherent framework. In M-theory, strings were not just strings. They could also exist as higher-dimensional objects called brains. The universe itself might even be a 3-dimensional brain floating in a higher-dimensional space. The most striking feature of M-theory was that it seemed to naturally include gravity. Unlike other quantum field theories, where gravity had to be forced into the equations, string theory predicted the existence of the graviton as an inevitable consequence of string vibrations. This was no coincidence. It meant that gravity was not an outsider force. It was built into the framework from the beginning. The final puzzle: is string theory the ultimate toe? In recent years, new mathematical breakthroughs have suggested that string theory might not just be one possibility for unification, but the only possibility. A 2024 paper argues that if we demand a self-consistent quantum theory of gravity, one free of infinities, then the structure of string theory emerges as a necessity. In other words, strings may not be just an elegant solution. They may be the only way nature can function at the deepest level. But what if the entire premise is wrong? What if gravity is not a quantum force at all? Some physicists believe that quantum gravity may require a fundamentally different approach, one that does not rely on strings. Others argue that we may never be able to experimentally verify extra dimensions, leaving string theory in the realm of elegant mathematics rather than empirical science. Yet the allure of unification remains. If string theory is correct, then all the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, are manifestations of a single fundamental entity, a cosmic symphony of vibrating strings. If we could see reality at its smallest scale, we would not find indivisible points, nor chaotic randomness. We would find harmony, woven together in the delicate dance of strings vibrating through the dimensions of existence. The universe, it seems, is not a collection of separate parts, but a single, interconnected whole. And string theory may be the key to understanding it all. The search for a unified theory is more than just a quest for equations. It is a journey to understand the very structure of reality. From Einstein's relentless pursuit of unification to Veneziano's accidental discovery of strings, and Witten's grand formulation of M-theory, each step has brought us closer to a fundamental truth. The universe is deeply interconnected, governed by principles we are only beginning to comprehend. But the final answer remains elusive. Is string theory the ultimate framework, the true theory of everything? Or are we still missing a deeper, more fundamental layer of reality? The search continues, and with every breakthrough, we edge closer to the answer. One thing is certain: whether through vibrating strings, hidden dimensions, or an even more profound structure yet to be discovered, the universe speaks in the language of mathematics. And if we can decode that language, we may finally unlock the deepest secrets of existence. The question is not just whether string theory is right, but whether we are ready to understand what it reveals. Thanks for watching.